Welcome to Marine Tech Talk, a podcast about how Teledyne Marine's innovative technologies are enabling scientific discoveries and commercial tasks in the world's oceans and waterways. In this summer series of podcasts, we introduce the winners of our Teledyne Marine Academic Grant for 2020. This grant offers universities and institutions the opportunity to use several of our flagship products free of charge for up to a 6-month period to support their research programs. In this episode, we meet our final winner, Jonathan Wallen, a PhD student in mechanical engineering at the University of Manoa in Hawaii. Jonathan's research is in the area of autonomous robotics and dynamical systems. In his current project, Jonathan is using a Teledyne Reson Hydrophone to dock an AUV to a floating wave energy converter. Now here's our guest, Jonathan Wallen, with the host of Marine Tech Talk, Melissa Rossi.
Hi, Jonathan, and thanks for joining me on Marine Tech Talk. It's nice to have you here today.
Thanks for having me.
Jonathan, you're a PhD student in mechanical engineering at the University of Manoa in Hawaii. By the way, not a bad location to be in. Can you tell us a little bit about yourself and your PhD studies at the university?
Yeah, so I grew up in Hawaii, in Honolulu, and made my way through a bachelor's in mechanical engineering at the University of Hawaii at Manoa, so that's located in Honolulu. And I started working with some underwater AUV research. We were trying to do docking an AUV to a docking station, and that was in my undergraduate, and that was really a fun project to get started on. I also was able to intern at some ocean engineering companies, so I had a lot of this exposure to just interesting underwater robotics during my undergraduate degree. And then as I continued moving forward, I kind of found that robotics is a very, very interesting field. And I also thought to myself, now's the time to continue school if I'm going to ever continue. So I applied for a PhD from the University of Hawaii at Manoa, and I stayed with my advisor and continued the work that I started in undergrad. And then we're still working on this AUV technology. We've also expanded kind of the competencies that we've developed in this AUV technology to other robotic domains. We're kind of doing some baseline research for what I'm kind of liking to call dynamic rendezvous. So a lot about docking and interfacing two moving pieces, and how can you do mechanical control in those scenarios.
First, congratulations. You were recently awarded an academic grant through Teledyne Marine's Academic Grant Program. How did you hear about the grant program, and what were you actually awarded?
I'm pretty sure I had 2 or 3 colleagues email it to me because they were on a subscribed list, which I should probably get on after this. But so they emailed it to me, and then I filled out the application. It was a pretty easy application that encouraged me to apply because it's kind of not a ton of time, but high reward. And so worked out really well. And we were awarded 3 Teledyne Reson Hydrophones, and we can kind of explain later what those will be used for.
That's great. Actually, just so you're aware, we actually had a pretty large pool of applicants. So it wasn't like we had 5 people apply and so, hey, guess what? 5 people win. We had about 50 or so, maybe more applications come in. And I think out of that, we had, 5 or 6 awards that we gave out. And so you actually won one of them. So it's pretty significant. Whatever you wrote on your application obviously rang true with our judges. So here you are, which is great to have you here. I read a brief overview of the study that you're planning on doing with the Reson hydrophones that you were awarded through the program. Can you explain that study and how you plan to incorporate those hydrophones in your work?
Yeah, so I'll have to give a bit of a backstory kind of like context here, the hydrophones are actually acting as a small segment of our overall goal, but they're very important segments. So beginning with AUV docking, it's a very hard problem. There's a lot that you are not able to sense in an ocean environment. There's no radio frequency, so you can't use Wi-Fi, you can't use radio waves. You're very limited. So there's a lot of acoustics that are used underwater and inertial navigation methods. And you kind of have to use that limited perception to do a very high fidelity control task. That is getting an AUV into a very specific docked position so that it can charge and transfer data, or basically communicate. And so we began by looking at docking to a static station that was fixed or installed on the seafloor, or to a rigid structure in the ocean somewhere. And that has been investigated for about 20 years, since like the early 1990s. Woods Hole kind of was a founder in the AUV docking field. And so we were looking at that. We did a little bit of work here in Hawaii. It's not a bad place to do ocean testing. We have a lot of nice ocean that's pretty warm all year round. So we were working on that. And then we partnered up with Ocean Engineering Group here, and they're looking at hydrokinetic energy converters, or wave energy converters. And we were like, what if we just combine these two projects? So our initial concept was just to put our first docking stations on the bottom of their wave energy converters. And so the wave energy converters are a dynamic structure. They're moving. They, slosh around in the ocean currents and waves, because that's how they get their energy, from the kinetics. So that added a lot more challenge to this already challenging issue of docking in a low perception environment. And so now you have a docking station that's moving in 6 degrees of freedom, and we now have to get to this tiny target region on it with high fidelity of control. We don't want to crash into it. These AUVs are very expensive, and we don't want to bang into it, break our vehicle, break the docking station, things like this. So we're trying to do it in a very controlled environment, or a very controlled way in a non-controlled environment. One thing that helps with this control problem is having precise localization, or knowing where your vehicle is relative to something else. So in this case, we want to know the location of the AUV relative to the WEC, or vice versa. And so if we can have a very precise direction measurement and range measurement, we can perform very educated control, doing somewhat optimal control, and perform this task in a clean and nice way. And we've kind of showed this in some simulation, but to do that in the real world, it's hard to get that localization. And so one way to do it is with a short baseline or a long baseline of hydrophones, which is called a hydrophone array. And so you space out the hydrophones in a very known geometry, and you have a source of sound. And based on the known geometry, you can triangulate the position of the sound. And so that's what we will be using these 3 hydrophones for. So we're going to test them out in a few different configurations. We're planning to put the hydrophone in a medium baseline array on the wave energy converter itself, and then put the sound source on the vehicle, and then flip-flop that and play with both of them and see if we can get good results for that localization for either of the setups, and then kind of see how that will benefit us in actually doing the beginning to end docking procedure.
Very hard problem, one that the industry as a whole continues to struggle with, especially the dynamic portion. So Even from a fixed platform, it's still a hard problem, but certainly from a dynamically moving platform, that adds that many levels of complexity to what you're trying to do. So I applaud your ability to go after the tough ones. For the project itself, have you actually, or do you have a date for receiving the hydrophones, and also do you have a planned date for the first phases of your research?
Yeah, so I just got confirmation that they're shipping in early June, so then they'll be here, a few weeks after that. And this whole COVID thing has been interesting because we would have been working in lab this whole last few months, preparing, being more ready to deploy these things with our whole system. So everything's a little bit up in the air. It'll likely be late this year, 2020. So like November, December time, we'll actually get in the water, hopefully with our full system. As we get them, we'll probably want to do some calibration and initial data taking. So maybe just build a small piece of hardware that can house the hydrophones in an array in a specific geometry, and then take data, work that into our simulations, and then see if we can use this more accurate data to still get the same results that we're seeing in an ideal simulated environment.
So the COVID comment brings up a good question too. How big is your team that you're working with, and are you able to continue working right now? Do you have access to your equipment at all, and how are you collaborating with any teammates?
We do have access to the equipment. We can get into our lab and work on things, but we're kind of taking the approach of work from home as much as possible because that's what's being recommended, and it'll benefit the whole cause of getting back to work for everybody. So we've kind of slowed down on the actual hardware side of things, which unfortunately, we're receiving this equipment, this hardware from Teledyne. So at some point we'll get back in there, but we have been working on as much of the software side and the simulation side of things as we can over this period of stay at home. And so our team is not too big. We have like 2 people from our group on the mechanical engineering side working on this topic, and then the one group that we partnered with, and one primary other student that we're working with in the ocean engineering side of things. So we're a small team, but the nice thing about being at UH is there are a lot of resources. The School of Ocean, Earth Science and Technology, SOES, like the counterpart from the College of Engineering here at UH, is fantastic. They have a ton of resources, like world-class ocean observing sites and boats and marine centers. So we have a lot of support from those facilities and that infrastructure, which is really nice.
So you're not going to, potentially be deploying until later in the year. I think you said November, December. Are you anticipating any specific challenges to that time of year in the waters there, or is that actually a good time to deploy?
It's the roughest time of year to deploy, but Honolulu being on the south side of the island, it's not as bad. A lot of the heavy seas end up being on the north side of the island, and we're kind of protected down in Honolulu, which is nice. And that is where we're planning to test. There's a site that's being developed. It's a nearshore cabled observatory. It's kind of being brought back to life a bit. So we hope to test out there, and it's close to shore, within a kilometer or 2. And so it should be good enough sea conditions to get our testing in.
Did you say that you've done some testing in theoretical models at this point for your plan?
Yeah, so we've done simulated docking in this way. There was a paper that went out at Oceans in Seattle. So we did some preliminary simulation on how to do this docking and running an optimal solver for the control. Our approach to solving this problem is we assume that we know something about the motion of the WEC, the wave energy converter. And we call that a model, a dynamic model. And so we can take that model and plug it into our solver. We take the dynamic model of our vehicle and we plug it into our solver. And then we take this localization information that we've been talking about, plug that in. So we're plugging a lot of things into this. Basically, it's an equation, and then you let the computer run iteration after iteration. And it's a numerical process that we could describe, but it's, kind of intricate, but it does different tests and sees if it's good. If it's good enough, it puts it into a bag of potential candidates. If it's not good, it kicks it out. And then it keeps narrowing down that group of potential solutions until it gets to one that's good enough or within our tolerances. And it ends up using that solution as the control scheme to get the vehicle from the starting point to the dock itself. So what we're really going to be interested in at looking with these hydrophones is, can we duplicate what we've assumed in our simulation? So can we get good enough data that we've been assuming we would have and using to get our simulations working?
Does the company that you're partnering with that's making the wave energy platform, you said they were able to provide a model for you as far as its motion in the water? So that's pretty well known?
Yeah, so it's actually another lab group from UH in the School of Ocean and Earth Science and Technology, SOES. So it's the Ocean Engineering Department, and they are working on a renewable energy wave energy converter. It's a unique design, so it's kind of fun to partner with them because they're doing a lot of fundamental research on their actual WEC, and while we're doing fundamental research on this docking challenge. And yes, they have done a lot of modeling of their system, and so we're getting motion models from them that we're working into our solver. And so we're trying to keep our simulation as real world as possible.
Sounds like a good group to partner with.
Yeah,
especially they're local, and they've got some data already that they've looked at for their platform. Any other challenges or things that you're expecting to find when you deploy? I don't know whether you have any theories about the way this is going to work or what you'll learn from it.
Yeah, I mean, from my experience with working in ocean things, is it's really, you can have a lot of really fancy theoretical ideas and mindset when you're in the lab and working with simulation, but the ocean is a whole nother beast. It's hard to model everything exactly, and oftentimes when you're out doing your tests, you're kind of faced with these, like, you bring it from the lab to implement it in the field and something doesn't work, so you have to come up with just like a brute force patch to get things working how you wanted to see them. And then you have to take that back to the lab and go, why didn't it work, and stuff like that. So I'm sure there'll be some of those patches that have to happen when we're actually testing. But, we'll try to see as much of that ahead of time as we can.
Well, I can already see that you're well conditioned already for this particular industry, because that's pretty much how we all operate. There's so many unknowns, and we can anticipate many of them, but obviously not all of them. So finally, I have to kind of close on this because I thought it was interesting. I noticed in your bio that you are roughly expecting to finish your academic work in the summer of 2022, and that you're anticipating a move to the private sector. Just out of curiosity, what would your dream job be?
Growing up, it was always a NASA job.
Wrong direction.
Yeah. So I was always in love with space, and then I found this underwater vehicle domain that's like, they're pretty much the same thing. They're both like, you're in an environment where humans can't live, you have to use robotic or, very controlled environment systems like a submarine or a space shuttle. And so people always ask the question, like, what do you want to do when you grow up? That kind of thing. If you grow up, I guess, is the other thing. But I always answer, like, I just want to do something that's fascinating, that's interesting, that's hard. And I think both this underwater domain and the space domain offer these challenges. When you're not able to be there, you have to have a very competent robotic system, and you have to implement novel, groundbreaking design. You have to come up against these challenges that seem impossible for decades. And then one design works and it breaks the door open for us to enter these domains, And so my dream would be to be in a position where we can continue to break down these barriers and provide technology that lets us go into places where we weren't able to before.
Yeah, that's really good. As a matter of fact, the funny thing that you just said, which was comparing space to the ocean as far as very similar challenges in both environments, very different environments, but very similar challenges, happens to be, I think, probably the second or third slide that we always use in our corporate overview, because Teledyne as a corporation does a lot of things in space. We have products on the Hubble telescope, on the Mars rover, and so many of our divisions do play in space. And of course, our whole marine division plays in the water. And we always have that. We have that slide that compares space to ocean and all of the challenges that, while different, really match up quite nicely. So it is funny that you said that. I want to thank you for being on the show and taking time today. What I am hoping is that when you complete your study this fall, that I can have you back on the show so we can go over what your findings were and see how it all turned out. Sound okay?
Definitely.
All right. Awesome. Thank you again. I really appreciate your time, and best of luck with your PhD studies and with this project.
Thank you so much.
All right. Thanks.
Thanks for listening to the Marine Tech Talk podcast. For more information about Jonathan's work on AUV docking, check out the notes for this episode in your feed, and you'll find links to his LinkedIn page, as well as the official webpage and Twitter feed for the Robot Autonomy and Navigation Laboratory where Jonathan works. We also have some links where you can find information about the engineering program at the University of Hawaii. If you have any questions or comments about this show, you can email host Melissa Rossi at marinetechtalk@teledyne.com. If you like this podcast, please make sure to subscribe on Apple Podcasts or wherever you're hearing the show. That way, you'll never miss an episode. Thanks for listening, and we'll see you again next time.